Hello and welcome back. So last time I was talking about the decomposition of the error, and we say that error is nothing but the differential between the true output and the expected output. So in practical you won't find a ML model that perfectly solves our problem. So it's very difficult to find a particular model where it will be able to solve all kinds of problems. It's nevertheless possible. So without making even a single mistake, and no matter how small the error could be. Since every model make mistake, it is critical to understand the nature of the error, nature of the model which produces the error. Suppose that our model predict a value and we know the real value. If the prediction is incorrect, then the difference is between the two prediction value and the true value is very simple. So I say error, I define in a simple term, error equal to real value minus the predicted value I have. So I have, on the other part of this error can come from the imperfection in our data. So data collection and data accuracy is very important, especially when a model is being trained. Okay. So another part of the error may come from the imperfection in our data set also, which I am going to discuss little later, and some form of imperfection in our model itself. That means whatever I am showing as an error formula, it also has something which is a unseen errors. Okay. So no matter how complex our model is, it can only reduce the modeling error. So I am trying to reduce the modeling error using the formula equal to real value minus the predicted value, and that is what the job of a error detection and correction algorithm. So irreducible error is out of our control. So I am using a term called as irreducible. Irreducible means the error which cannot be reduced. For example, the error arose because of the imperfection in the data, error because they were impregnated because of the imperfection in our model. So those kind of errors are usually termed as irreducible errors, which are beyond our control. So let us go here. So we define the problem of error using a modified formula equal to error equal to error underscore reducible plus error underscore irreducible. So you can see that the reducible error is nothing but y minus y hat, and irreducible error is because of the imperfection in the data, imperfection in the model itself. So let us try to understand the error in a perspective way. Not all reducible errors are the same. We can decompose reducible error further. For example, look at the following diagram. Now I have a bull's card, a bull eye, and I have a target equal to the circle shown in the pink dot, and I have a dot which are basically shown as a blue, and they go in the outer circle. Okay, the periphery is bigger. So what is the error? So the red center of each target represent our goal, and that is what we call as a real value. So my real target is my red circle, and that is what I am expecting a model to predict. However, the blue dot or blue shot represent the model prediction. So model has predicted or given me something like here. Okay, the model aim is very much off. All predictions are close together. So I have 1, 2, 3, 4, 5 predictions, and all these predictions are very close to each other, but the error is very high. Okay. So the model's M is off, all predictions are close together, but they are far away from the target. And when they are far away from the target, it is very difficult to identify. So this kind of error is called as a bias. So my predictions is more or less biased around 1 and 1 and 1 only. So the simpler our model is, more biases or more bias will have. So for a simple model, bias component can be a prevailing thing for us. So let us go here and let us try to see the model. For example, if we plot the model as a complex relationship between variable with a simple line, this model has it. Okay, so I have on x axis, I have on y axis, I have a blue dot and my linear line is going. Okay, so some of the points are lying okay, you can see that most of the points are lying above the line. So when most of the points are lying above the line, I have a problem. The problem is because the model is more biased toward this data set rather than in this data set. So it is not able to identify the data points which are here, or it is giving less error here, less here, but error is more concentrated on this side of line. So this is what we call as a bias. Now when I have this kind of bias, okay, the second component is what we call as a variance. Now if you see the variance, some of the blue dots are close to the red one, but some are little far away from the red dot. So the variance is here very high, but in the earlier case variance was very low, because all the points or all the dots put together are having a cluster together. So variance is another term we need to define and we need to understand. So variance tells me a very important thing called as a, so what is variance? All prediction appears to be clustered around the true target. So you can see that I have a true target here, I have blue dot, blue dot, blue dot, blue dot here, but the variation or variance from this to here is very low, smaller, getting more small, I mean getting little more than smaller and things like that, but it is not definitely clustered here. So all predictions appear to be clustered around the true target. So here the cluster is more or less targeted toward the center, but the spread is too high. The source of this error come from the model sensitivity to the fluctuations in my data collection. So this is the real world example for weather forecasting or temperature recording or finding out the sentimental analysis of the people who are on the fly. So things like that, where the data is of a more fluctuating in nature. If the model has high variance, randomness in the measurement can lead to a different predictions. So this is a consequence of my error. If my variance is very high, I may predict, model may predict something very good, sometimes very bad. So this is another problem of our model prediction. Okay. So far we have decomposed the error into this form. So we say error equal to bias plus variance plus irreducible error. So we have to more or less talk about two components only, bias and second component is variance. So we use a word called as bias variance trade-off. What I want a less bias, more variance, I want a more bias, less variance, or I want both less or I want both more. So this is what we call as a trade-off. So it is not a coincidence that bias and variance sit close together in the same formula. There is a relationship between them, and predictive models show a property called as a bias variance trade-off. So what you want, the more bias a model has, the lower the variation component will be, okay, in the error, and in reverse, the more value of variance it has, the lower bias it will have. So it will be a something like our formula like a exponential decay. So this is important fact, will be game changer for a building a ensembling model. So especially when I am doing a model ensembling or trying to put a model, 2 or 3 models put together like our forestry, okay, where 3 or 4 trees are being combined together. So the complete model accuracy has to reduce. So this is how we do it. So typically models that impose some kind of structure in the data have a high bias and they can be assumed a data to confirm. So we, for example, I have a formula, housing price is equal to $10,000 into number of square feet. Now if you look at a price as a model equal to 10,000 multiplied by this. Notice that if we change the square footage by a little, let us say I change the square footage by 0.1, then the prediction won't change much. Okay, this is thus the model has low variance. When the model is sensitive to changes in the input, its variation will outgrow the bias. So the variance component will grow when your model increases in complexity and the total number of parameter is grows too. So this is what we call as our model, and you can see here a model which is a simpler one, will have a more or less both the side fluctuations, and this is a best fit, and a model which fitting all the data in a zigzag manner is what we call as a overfit. So in the next lecture or in the next session, I am going to talk more detail about the overfit and how to avoid a overfit in the data model. So thank you for patient listening.